Hello, everyone. Welcome to our workshop, which is part of the Hamlyn Symposium on Medical Robotics. Thanks a lot for joining. So I see participants are coming in. We are already on 38, but I suppose a few more will still join. Nevertheless, let's get started. My name is Caspar Althöfer, and we have I think, a very exciting workshop today, which is obviously related to medical robotics. Our workshop is on soft, smart, multifunctional, agile, and aware surgical robots. And we will be talking today about progress and technologies. So in line with the organization of workshops at this symposium this year, our workshop will go over 3 days. So today we have day 1, and you can see that on the screen. And the focus will be on soft robots, actuation, implementation, and clinical translation. And if we go to day number 2, then we can see there, it's not coming out, it's coming up now. Day 2, that is tomorrow, will be on soft sensors for soft robots. And then finally on Friday, day 3, we will be talking about modeling, learning, and control of soft robots. So really a theme around soft robots and how we can apply that to the problems or different problems in medical robotics. So if we can bring the screen back again to the first one, maybe again, I just would like to give a bit of an outline on what we have today. So we have a number of exciting talks today, 4 talks, and we have 1 hour for these talks. So each presenter will have half an hour to present. And so I would suggest try to, keep it to 20, 25 minutes. And then we have time straight away after the talk for some questions and answers. And I would like to add to that. Please do raise your hand if you want to ask your questions through the microphone, or use our Q&A chat box to type down the question there, and we can then present that to the speaker. Good. We have also a number of posters which we will present. More details will follow on that while we go along. So I think I'm on the spotlight now here. I should also mention that if everything is being recorded. I suppose Zoom announced that to you already. So everything will be recorded and will be also available afterwards. So really focusing on soft robots, flexible systems, stretchable electronics, and also sensors that can be then applied or integrated with these kind of soft structures, and how we can now move forward and create devices that are suitable for medical applications. And so today, really the focus is on soft robots themselves and the actuation of those, implementation, but also looking at the clinical translation. So we have engineers here, roboticists, but we also have Alberto coming with the talk at the end, Alberto Arezzo giving the clinical perspective. I should also say that my co-chair is Helge Wodemann from UCL. So great to have him here on board to chair the session with me. And he's also there to correct me if I say anything wrong. But I hope so far everything was fine.
Good afternoon. I think that was a very good introduction to the entire workshop, and I'm very happy to share this today with you.
Thank you. Yeah, fantastic. Good. That brings me also to something else, which I was told I should highlight. So we have 3 parts to this workshop, and today is day 1, tomorrow is day 2, and then on Friday is day 3. And each workshop is 2 hours long, and you will need to register for all of them. Yeah, so sorry about that. So you registered successfully for this one today. I can see you here. But if you want to also join on Thursday and Friday, you will need to register for those as well through Eventbrite. Yeah, sorry for the extra effort needed there. Good. So today we have 4 fantastic speakers. So we have Hongbin Liu, whom I know for quite some time from when we worked together at King's College London, Kabai Kwok from the University of Hong Kong, and then later we have Ariana Menchassi from Scuola Superiore Sant'Anna, and at the end we have Alberto Arezzo from the University of Turin. Good. So I think I have covered all aspects, and I would like to give the floor now to Hongbin Liu. Great pleasure to have you here, and I look forward to seeing your newest work. It's all
Thank
yours.
you. Thank you, Caspar. Thank you. So can everyone see my screen now?
Yep, we can see it. If you can, yep,
Okay.
we also see it in the right mode. Perfect.
Okay, right. Hi, everyone. It's my great pleasure to be invited by Caspar, my old supervisor, and my colleague Helg to be in this workshop today, and then talk about our work on a self-propelling robotic endoscope. The name, we name it MorphGI at King's. So today my talk is hopefully to show you guys a journey we have been through in the past few years, and then basically we're trying to teach a soft robot to perform colonoscopy. So these projects we have been working with King's College Hospital, the gastroenterology department. In the past decade, we see a sharp rising demand on the endoscopic unit in the UK. So we see in the range of 11 to 15% increase per year. This is due to the increasing awareness of GI disorders and the screening participation. So particularly the demand for lower GI, basically the inspection of your colon, are increased more than 100% between 2013 to 2019 in the UK alone. So this data is a little bit outdated. So basically, it is estimated that in 2019 to 2020, the colonoscopy in UK itself is around 1.4 million. So it's quite a big number. At King's College Hospital, our collaborator site, their endoscope units see a 14% increase per year. So it's a quite substantial increase, and then the doctors are working basically over weekend to try to meet the demand. So they are really short on the staff, and also the current colonoscopy procedure are not very comfortable to patients. You can imagine when you inserting a semi-rigid tube into the colon, it stretches your bowel and then the nerves, so it causes a pain sometimes incidents as well to patients. So really, the clinicians we spoke about, they all want their colonoscope can do something like this guy. So they want their scope can be solved, so generating less force to the patient's colon. They want ideally they want the scope can propel itself into the colon instead of being forced into your organ. That will require less skill for the training, and basically means more staff can perform colonoscopy. Ideally, they want their nurse can do that instead of them doing, tens of cases per day. So we have been basically thinking about how to make their kind of a dream into reality. We tried many ideas and many failures. So in the end, we arrived to a solution like this. Basically, it is a soft endoscope made with 3 soft segments, and each segment is able to bending in all directions, and when it works, it's basically try to mimic a inchworm's a way of moving forwards. Basically, it's bending its front segments to try to hook on the colon's wall, and using the middle segments to push itself forward, and then use the rear segments to anchor on the colon again. So by doing this in the kind of a iterative order, it can propel itself into the colon without the clinician pushing it through. So because it's a robotic device, so it's very easy to be controlled. So it's more intuitive than the conventional colonoscope. So here is a comparison what happens when you use a conventional colonoscope, what happened inside your gut. So basically you can see if it doesn't propel itself, then you have to use the colon wall to force the scope into your colon. So, and also using the soft material, there's another additional advantage. Basically, we have a large bending radius. So that's basically make the inspection more, give the clinician more freedom of inspection. So basically, there's another advantage, not really, probably we talk about less in research community, but mentioned a lot about in the clinical community is the single-use aspect. When you use a soft material, one advantage of social visit is that the cost can be made quite low. That's basically you can allow you to through the scope after each use, and that's have a big advantage of eliminates the cross contamination between patients, and also reduce the basically eliminates the need of a special facility to clean the scope after each use. So that's another associated benefit with it. So when you see this video, so this is basically the real device. So we can see that it's really flexible because that's the property basically given by the soft material. And sorry. And it's the high angulation angle is a very nice feature the clinician wants. And it has a 3.2 millimeter instrument channel, so you can pass through a regular biopsy tool. More importantly, we realize the cell proportion, so you can see in the video in the right bottom corner. Basically, the robot can propel itself through this training phantom without being pushed. So it's basically crawled by itself from the beginning of the insertion to the end of the column. That's what the device can do by basically manually. So basically what you see in that video is a operator teleoperated robots trying to moving into the column. Here we also have been working with IBM trying to make a semi-autonomous guiding system. So the idea is in the future we want the clinician can be free of the hassle of pushing the tube in. They only need to do the inspection. So that will make them more focused on their real job is try to find polyps, tissue abnormalities during the inspection. And because this will de-skill the endoscopy procedure, so that's basically can increase the accessibility of this service to more facilities. So we have been working with a group of IBM trying to make a AI guidance system. So here we can share some results here. So basically we made a, we call it Amy, a smart guide. Basically it's a group of people in IBM working on the machine learning side. We are providing the robotic device, and input into the system. So basically, it requires the video frame from the camera and also the coordinates, basically the motion data from the robot. Then basically they through their algorithm, they will generate a command to control the robot. So what they basically trying to do is to try to, if in this video you can see, so basically their algorithm is trying to find the center, the central line of a of the column of the tubular structure, and then basically select the right time to push to make the robot moving forward without hitting the wall. So that's basically what their algorithm does. And you can see that this is a fully automatic procedure. So basically, you can see that when we turn on the guidance, the robots can basically autonomously moving from the insertion point to the end of a column. And so we also record the time as well. So it's about that time is about 10 minutes. We can do the full autonomous colonoscopy from the beginning to the end. So we all see that we believe using soft material and make it self-proportion can significantly reduce the force applied to the column. But we have been trying to find a way to demonstrate that. So we've been so therefore we have designed this force sensing phantom. So you can see from this picture. So basically, we bought a off-the-shelf colonoscopy training model. So it's a rubber model, and then we shape it into a typical column configuration. And we basically designed 7 force sensors and then place them at the critical locations. Normally, the clinician recommends this is where they feel during the colonoscopy they will stretch the bowel particular hard. So basically, you can see from here we have one sensor at the sigmoid column, and we have a couple of sensors at the descending column, and we have one sensor at the splenic, they call it splenic flexure, and another one is at the hepatic flexure. So then during the test, we have this elastic band to connect with the column wall to simulate a membrane tissue you will see in the real column structure. So to do the comparison, we tried a conventional. So we first used a conventional colonoscope, a Fuji 11.8 millimeter colonoscope to try let the clinician finish the colonoscopy, and then we then evaluate the robot in the same phantom. For this for the colonoscope they have 2 stiffness settings. So this is a relatively new design. So you can basically set high stiffness and low stiffness, and we compared in both situations. So when we did the test, so basically, as you can see from this figure, so we first insert the scope into it from the rectum, and then basically we're pushing through from 1 to 2, 3, 4, and then we retrieve back. And then during the whole process, we measure how much force experienced by the force sensors. So here it shows the typical scenario. So basically, you can see this is the force experienced during the colonoscopy. So compared with the 5 locations, you can see the most of the force are experienced at the sigmoid and the descending column part. And here is a more interesting result. So basically, here it shows. So the blue line are the force measured by using the high stiffness setting of the Fuji colonoscope. The red one shows the low stiffness setting on the Fuji colonoscope. You can see there's a big drop in terms of force implied to the column wall by using 2 different settings. But more interestingly is when we use the MorphGI, so our robot, it's significantly lower than the lower setting of the Fuji's scope. Here is a more detailed comparison. So basically, you can see in every locations the MorphGI's force is significantly lower, except the initial phase, which are basically there's some learning curve. The clinicians are not very familiar with that part, so they are trying to push the scope a bit hard. So this part is not as smooth as when they use the tool they get used to, but still the force are not really high. The biggest difference it happened at the phase 4. So basically you can see the MorphGI really low, and then the normal scope are quite high. So here is the in the descending column, it's more obvious that the conventional scope are much higher, generating much higher force than the robotic one. So so basically in a summary, you can see that so basically compare with the MorphGI, which is these two data, we can see that the force generated by the robots compared with the conventional scope, we can achieve around 80% reduction of the force applied to the column wall. So I think we are pretty happy with these results, which basically demonstrate that I think one advantage of using soft robot in this particular clinical application. So here is some pictures we took during the colonoscopy, and then you can see that you can even see the difference between the using the robot and the conventional scope. So this is a conventional. So this is what happened when you use a conventional scope, and you can see the bow is stretched quite. It's quite significant if you ask me. And then so basically at some point we need to ask a nurse to pushing this part to make the conventional scope to pushing forward. It happened in both cases, but in the robotic case we don't need to do anything. So the robot just passing through without problem. All right, so I think that's the end of my introduction. One thing I also want to mention is that we also now recently checking to compute the in terms of the speed. So on average, we are now able to achieve we are now able to finish a colonoscopy in the simulated column in 8 minutes, which this is comparable to the UK's national statistics. Normally in the UK, we check the data is finished within 5 to 10 minutes. So I think we are in the comparable range. Obviously, there's a lot of things need to be done to further pushing this device into a real clinical use, and we are in the process of doing animal trials, and hopefully we will be one day we will be able to get this device into the UK clinician's hand. Thank you.
Thank you very much, Ongbin. Fantastic presentation. I'm really impressed by the progress you made.
Thank you.
At St. Thomas Hospital, I suppose, which is part of King's College. Yeah. So thanks for giving this fantastic overview. And we do have some time for questions. So if I maybe can start by just looking at the Q&A, where we have already some questions that came in. And so I start with Karthik C, who has asked the question, could you please explain the advantages of colonoscopy over capsule endoscopy?
So the one big advantage that this device can do therapy. So we can equip it with basically instruments to do biopsies, and then also this can be extended as a surgical tool. Another potential advantage, which I'm not have evidence to support, is, I think, likely using this device is quicker than the capsule. Especially the colon has many different folds, so that's a little bit challenge for capsule type of device to be able to pushing through. So that's quite challenging.
Thank you very much.
Yeah.
Another question from Andy Wu. And the question is about, I suppose, the instruments that you're using there. So what is in the end of the endoscope? I suppose he's referring to your colonoscope system. And he says further, it's like sticking out twig.
So that the so currently, so the scope itself is basically a camera with a hole for passing through instrument. So the instrument we demonstrate in the video is a standard biopsy tool they use during colonoscopy. So basically, it's taking a little bit bite on the tissue and then take it out.
Yeah. So I suppose it is pushed through the internal lumen.
Yeah, lumen. Yeah.
Colonoscope, and then sticks out at the end, possibly looking a bit like a twig, and then can be used to manipulate the tissue. Yeah.
Yeah.
I suppose. Yeah. I have some more questions which I will ask, but in the meantime, I would like to also encourage everyone to either put questions down in the chat or raise their hand. I haven't seen any.
May I ask maybe Fun to ask the question if you like.
Say again.
There's one raised hand.
Oh, there is a raised hand. Okay.
Yes, and we can ask the person to unmute and share their screen or share their camera if they would like.
Hello, can you listen to me?
Yes, we can.
Yeah.
Hi, Hongbin. It's Van.
Hi, Van.
How are you?
Hi, Van. Yeah.
Long time no see. Yeah. Hi.
Yeah.
Hi, Goodman. Hi, Caspar. Okay, so I'm not sure if you see me now, but
I can hear your voice.
No. I don't. Yeah. Anyway, so very nice talk about and this work, and I'm very happy to see you really move forward in this direction. And I actually have some look at this technology. So I have some just comment or like question. First, so you compare the your developed one and the normal one, right? So I'm wondering, so when you conducted the experiment, so who was the one that's extrude the colonoscopy device into the phantom column? Is it a well-skilled doctor or
yeah, it's a well-skilled, yeah, it's a well-skilled doctor. It's their department head of the endoscope unit. Yeah.
Okay, so I think that's a very good point. Yeah. And so the other point is so usually I see patient, right? So they're not lying like horizontally on the bed. Usually they lie sideways, right? Sideways.
Yeah.
So there's one part of the column that is vertically located. So how your robot can,
moving vertically, you mean?
Like move forward, with the effect of the gravity in this case.
And
have you tried that?
Oh, that's a good point. We never tried pushing the phantom in the kind of a vertical sideway. Yeah. We did test the friction though. So it generates about 2 to 4 Newton friction, depends on different kind of a configuration of the column when we test it in the phantom. So we think if we lubricate the scope well enough, it probably should be fine moving upwards.
Yes.
Yeah.
So okay, so that's something I'm wondering now, and I believe you also can solve it right way anyway. So
thank you. Well, this is a good one. So we never actually tried to work to make it climb vertical. Yeah.
Okay, nice. I'm looking forward to your paper.
Thank you very much.
Thank you.
Fun and greetings to Japan. I would
Yes,
like to just, before I give back to Caspar, to ask this question from Xu Chen, who would like to have more explanation on the haptic sensor system and how it works. And maybe I first of all want to congratulate you, Hongbin, on this fantastic system and the presentation as well. And asked on top of this question if you have also looked into stretch sensors, as the strain is probably also harm or imposing pain in a sense.
Yes, that's a very good point. So to the sensor part. So as we have been working with Caspar for many years, so we are able to normally make our own sensor. But I think that's not part of my talk today. We had a lot of discussion about having strain sensors instead of basically the single sensor unit. In the end, we didn't use the strain sensor because for the design we discussed that we think there's probably too many wiring issues if you connect the strain sensor. Normally you need connecting wire on both sides. One advantage of using a single unit is we can centralize all the wirings into the middle and hide it underneath the box. So I think that's probably the reason we didn't choose the strain sensor.
Thank you very much. Over to you, Caspar.
Yeah. Okay. Yeah. No, thank you. I have also a number of questions. More on the technical side, and I don't know whether you can give more details, but it was not too clear to me how you do the anchoring and how you then do the actuation that kind of moves, this peristaltic kind of motion that you achieve then.
Sure. We are using, first we are using hydraulic. So basically we're pumping liquid. As you know, before during Stifflop, we already start looking into using liquid to actuate it. To make it anchor, so it's also not so difficult to explain. So basically, when you bend the segment, obviously you have to make it in a particular stiffness, but when you bend the segment, it kind of like finger pinching the soft tissue, so that's generating a anchoring force.
So you pinch a bit of the colon wall, yeah.
So it's generally it's like that.
Okay, good. Yeah. We can maybe go over to another question, which disappeared.
It was the same question, a very similar question that you just asked. So
okay, good.
I would give to Kai Wai, who also has a question before we move on to our second.
Hello, thanks Hongbin. Very nice talk and very impressive result. I can estimate the difficulties throughout the journey. I can see the very fantastic kinematics performance. But I heard of a lot of endoscopists. Somehow they doing the colonoscopy, the tunnel may not be very clear, and somehow they need to use the scope itself, the body itself, to lift up the tunnel, and then that's why in your simulator have you implement with some apply some weight, dummy weight, let's say put it as a gust, put some bowen on the simulator, and then would you realize the difficulties? Is it really much more than the free one without weight? So this is the simple question.
Yeah. So how we tried to put some weights on before. As long as it's not massive. So basically we have a way to try to open up the tunnel is by putting more pressure. So basically you're pumping more air if you think the tunnel is too narrow. That's basically what we did when we see the tunnel is too narrow.
Great, Thank you. Yeah, definitely. I will catch you up offline.
Yeah, of course. Yeah.
This is amazing. Yeah, three segments. I can see the how the robot anchorage on the cones and then move forward, which is a very nice locomotion.
Thanks, Con.
Can I just have a quick follow-up on that one, also on a technical side?
Yeah.
I mean, I saw you have two approaches. One is the autonomous or semi-autonomous way of moving forward, and the other one is the operator controlled one using the camera for feedback.
Yeah.
But how do you calculate the inverse kinematics?
So the inverse kinematics, we are using actually for the AI guidance system, which we just use a constant curvature model, and then we kind of adapt a little bit on the 3-chamber actuation.
Okay, so effectively a model. I mean, constant curvature model.
Yeah.
That is useful to target the inverse kinematics.
It's actually, it works fine. Yeah.
Works fine. Okay, that's good to hear. Okay.
Yeah.
Thank you. Yep, I think we are good. I cannot see any further questions. Again, thank you to Hongbin. Fantastic presentation. I mean, I was super impressed and would definitely like to keep the contact and hear more about that.
Of course, yes. Yeah.
Thanks a lot for that.
Yeah.
And
I'm very happy to present this to you today. This is the first time I present this work.
Yep. Yeah.
It's on a special occasion.
First time overall that you presented, yeah.
Yeah.
Okay, good. Yeah. Thanks. Yeah. Thanks for coming to us.
Yeah.
First time. Yeah. Thanks a lot.
Yeah.
Good. Okay. Thanks again, and we move forward to the next speaker, and gives me great pleasure to introduce Kawai Kwok from Hong Kong, University of Hong Kong, and I know Kawai also for many years now. We had also already some collaboration. So, but I'm always fascinated by the work he's doing, and so I look forward to seeing your work today. And without further ado, I pass over to you. The floor is yours, and we can see a screen. If you go into the presentation mode, then
so I guess you guys can see my screen. Here you go. Here's Kawai from the University of Hong Kong. It's my pleasure to be invited by the organizer. I'm happy to see Hongbin's work, and then the topics here is about the online computational mechanics, and I guess Hongbin also did some computational mechanics or finite element analysis on his robot. So I suppose that robot is already passed the preclinical test and trial. And if even not, I'm happy. I'm volunteer to Hongbin to perform or to do some analysis on this one. So this is a kind of a journey. I studied these topics mostly from the control and computational point of view, and see whether I can foresee the further trend of the soft robotics development in the surgical applications. So if I move on, since the Stiffness project, actually there's many attempts using soft robot in surgery, and many of them will hypothesize the advantage in using soft robot. For example, the robot can be combined with various anatomies such as lumen, conal, or abdominal cavities. And those robots typically using fluid-driven approach to drive the bending or turn the camera perspective, acting as the endoscope or endoscopic instrument. So here is an example from Professor Wood groups from Harvard. The soft device can be very thin and small, capable to deploy from the standard endoscope. And there's another mock-ups here. So a device developed by KU Leuven, which was decided to operate inside the eyeball, and comparing to the conventional tendon pulling method, the soft actuation taking effect close to the end effector somehow enables more effective mechanical transmission through a longer path of tendons. So apart from fluid-driven approach, recently there are many advances in new functional materials to generate the delicate motion potentially for surgery. But I will not go through them here. I'm not a material scientist, but instead I prefer to look for any good hints from the regulatory point of view, which is the FDA. For example, how can we guarantee the manipulation precision, or let's say how any calibration procedure we can do for soft robot, so as to establish the robot to fulfill a precision criteria, stability criteria. Another concern is how we can demonstrate here the robot would not causing any unreasonable injury to the soft tissue. So it also recalls my works a few years ago. We developed a fluid-driven soft robot can manipulate and produce a very high payload. In this video, you can see the robot can lift up the things as heavy as a can of Coca-Cola. The inside pressure operates at 6 bars of fluid pressure. So the idea is that in typical vehicle types, the pressure is around 2.5 bars. So that is a very high one, giving out a similar bending effect as a conventional endoscope. But the thing is that if put it inside the bodies, when the robot got burst, would it be any kind of very strong impulsive fluid impact causing the injury to the soft tissue? This is the question I haven't validated. But for the robotics surgery, I also look at the more specific guidelines, also recommended by WHO. It specifies clear on the robot control latency, error, as well as the concern on the situation when the robot operates beyond its kinematics limitations or range. Generally speaking, reading those regulations, we will come up with a very tough question. What is the way out of soft robotics in surgery? And then how do we prove how do we prove soft robotics can outperform the rigid counterparts used in the surgical robotics, such as the tendon-driven mechanism? Controllability is always my concern. It's a very important dimension to validate the clinical values, pedicle values. Somehow the robot may not need to involve a very high-end materials or mechanism. If we can manage the soft robot control well with sensing feedback, the soft robot could be humbly small, do a little task, well beyond what the rigid robot can do. So this is an example I like it, and then I find it in ICRA, which is the research work done by UCL from Professor Sherlock groups. They use a very small robot. They drive the soft chamber pumping fluid inside to steer the needles. The whole entire robot can anchor it inside the ear canal. Tiny camera at the needles as a control feedback. They can use they introduce a lot of very interesting visual surfing. I can see many advantages over the tendon-driven or rigid robot mechanism in this example. So if I say control while dealing with robot control, definitely we have to incorporate our understanding of the robot. So either through the robot kinematics or dynamics, many roboticists have many attempts to approximate the kinematics model based on their geometry hypothesis. But however, the model can be rough, and since the assumption usually oversimplify the geometrical relationship, taking one example, piecewise constant curvature models, so-called PCC, let alone the assumption of the constant curvature or torsion bending, zero torsion bending assumptions, the errors still can be very much. The error from the material elasticity, fabrication error, tuning parameter will bring many sorts of modeling uncertainties here. So therefore, relatively, the data-driven approach will be a promising way out for resolving the nonlinear nature and also resolving some individual variation due to the fabrications. And also the soft robot characteristic can also be learned using the data measured or the data collected from the robot itself. This is so-called sensor. And however, the pure data-driven control mechanism, the pure data-driven control method require very high-quality training data, could not handle complicated untrained interaction with the surrounding. So the non-guaranteed performance would hinder the application in surgical robotics, because they somehow may not easy to ensure the safety standard. So analytical modeling is still necessary as a baseline for surgical use. So apart from the geometry hypothesis for kinematics model, there are a lot of also a dynamics modeling examples. Here is the one done by Professor Cartwell group, and the video present an energy approach. They try to model the robot to avoid the explicit formulation of the internal forces. And the Lagrangian mechanism is a classical energy method. They use it as in the models and represent the energy transfer involving internal forces or even the external forces due to the actuation and contact. So the system dynamics is governed by Lagrangian equations involving potential and kinetics energy. It can predict the dynamics response of a fluid-driven robot in real time by recursive optimization approach. And as you can see in this video, the simulation and the robot are synchronized very well and aligned with each other. And then you can see they are even the slightly vibration. You can see the robot actually, the simulation is very accurate. But however, the point is that how we can customize such an accurate modeling for various robot prototypes or individuals, and then utilize this method in the inner control loop so as to fulfill the real-time performance. So that method still need further investigation, but the simulation prediction is fantastic. To close the control loop, the most handy sensing device would be the RGB camera mounted at the tips. So this is a kind of eye-in-hand settings under the visual servant concept. In this experiment, my teammate implements a pure learning-based control method on a simple 3-chamber continuum robot. The deviation from the image center towards the target, tracking target, would be the error feedback. So the idea is to incorporate the online imaging data to replace those improper offline training set. So furthermore, to reduce the computational workload while initializing the models. And then here we try to divide the soft robotics workspace into many smaller submodels, and using the local Gaussian process regression, GPR, and so as to approximate the incremental kinematics of each submodel. The main advantage is that over the visual servant approach is that this is the end-to-end mapping, so as to represent the intricate modelings, and then also including the coordinate transformation, and also can bypass the high nonlinear soft robotics behavior. Even the robot is very floppy one, made of the silicon. So, however, data-driven approach is handy, but we still want to understand the underlying deformation inside the robot structure. And I believe finite element analysis, FEA, will be the best one to represent the complicated computational mechanics. So in terms of the application in robotics, probably this work from Kristen was the first attempt. He has incorporated FEA model in the real-time control to control the cable-driven robot. And then he tried to simulate more complicated interaction involving various composite materials, such as the hyper-elastic elastomer, fiber reinforcement, or semi-rigid backbone. The control sampling rate could be achieved to 20 Hertz. So if I move on, I also 2-3 years ago, we also proposed a practical offline finite element approach. Why I say offline? Because we want to use the finite element analysis to form a model without the prior knowledge of the robot kinematics. We just know the basic structure or profile of the robot and then do the analysis to initialize the kinematics model at the very beginnings. So later on, after the model initialization, we also increment the online learning approach on it. So the concept is simple. So we initialize the computational mechanics model by pre-training the simulation data from the FEA. So this is a kind of virtual operation of the robot-specific structure. Yes, that could be very rough, but the model can be incrementally adjusted by the machine learning approach. So throughout the online updating process, no kinematics model is necessary to be defined. So the most existing research, including ours, will focus on the control, mostly on the robot end effector only. But in the previous visual serving examples, the block of features could be tracked to the image sender. It was actually our control objective. But however, somehow the control task can be applied on only end effector, decoupling from the robot body. If going back to the case, like a Hongping's example, he also used the robot body to anchor along the condo. So that kind of control may be also important rather than just on the end effector. So the actuation in the continuum structure will also affect the overall deformation. That's why this is also critical to take account of the robot configurations. So that's why we also did the shape sensing rather than just the positional checking on the end effectors. So so here I'd just like to introduce a very handy solution, which is the optical fiber gratings FBG, which is a shape sensor that could be self-contained in the soft robot. In this diagram, you can see there's one piece of single fiber can be wrapped on the robot on the symmetrical surface of the soft robot, and that fiber can contain many FBG sensors. And each of the FBG can be added with the local change of strain or deformation by reflecting a wavelength shifted light. So in this case, we can use some external tracking device, for example, 3D camera, EM tracking, electromagnetic tracking device to track the shape. So now in this diagram, I just like to show you how we employ the neural network, deep learning, or AI approach to train the mapping from FBG data to the resultant robot shape tracked by EM tracker or 3D camera. So this video shows an example of a soft robot configuration sensing in real time. We employ the learning-based FBG model for the robot shape predictions. So on the left-hand side, you can see during having the offline training, we can update the soft robot configuration in real time, and even you can see the vibration is doing very good jobs, vibration detection. And then on the right-hand side, you can see we can do the 2D image mosaicing in real time. Based on that FBG sensing, even we apply some external disturbance on the robot body, we can stabilize the image mosaicing very well. So actually in this research, FBG is utilized as a real-time strain sensor. The offline FEA plays a very important role to initialize the models. Using the FEA, we can know the possible robot deformation workspace in advance, and also mostly importantly is we can have a unit mapping between the FBG string data and the robot configurations. So in this work, eye in hand camera data provides an end effector process. So our hypothesis is that we can train the FBG data model online to predict the same camera pose, to predict the same end effector pose simultaneously. So provided with the sensing fusion with FBG and camera, we can even while in some situation the camera cannot perform very well, the camera pose estimation deteriorate by the poor imaging quality, the FBG can act as a accurate alternative. So the demonstration is the overall performance of the hybrid control framework. We try to fuse two sensing data together from camera and FBG, and then so as to find enrich or improve the pose estimation. And then in the end, we use that pose estimation to improve the outcome of the mosaicing, image mosaicing. So although I did say FEA is a very good ultimate tool to model the robot deformation, actually there's many challenges in performing FEA online, so as to provide the certain level of real-time robot control standards. So the first challenges comes from the materials themselves. The two properties make it very difficult. One is the composite materials, because when multiple material combine together, that makes the FEA's representation models tessellation very difficult. And the other is the hyperelasticity of the material that mostly the soft robot will made of. So secondly, the choice of tessellation will determine the primitive form of the soft robot. It could be very crucial for simulation result, and somehow it could be a trial and error requiring a very empirical procedure, either the improper choice of element types or unmatched tessellation will cause the very bad error, invalid or non-convergence situations in FEA optimizations. Finally, the computational cost is always a limitation. Actually, hyperelastic FEA would involve a long iterative operation or optimization. Even somehow that could be accelerated by the parallel computing using FBG, a GPU. The computational demands is still very intensive to meet the real-time standard. So there's some example regarding the very computational exhaustive procedure, which is a compressive sensing in MRI, which is I know more. I'm not going to go through in detail, but just let you know. Someone 2 years ago, someone published in Nature. They tried to use AI to do the end-to-end mapping, so as to successfully bypass that kind of very iterative approach, very intensive approach, and then successfully can model the mapping in between the frequency domain to the image domains work. This is a amazing work published in Nature, demonstrate the end-to-end deep learning performance in such a very clumsy, complicated computational process. So at that time, my question is, why not we can't do it on FEA? Until very recently, there's a one just published in Science Advances. This is kind of as a pioneer example showing how the AI works as a surrogate of a conventional FEA in solid mechanics. I repeat, this is just solid mechanics in 2D cases. As you know, deducing the material properties will be experimentally, even the computationally troublesome. It successfully estimates the stress strain fields of 2D composite materials. And also this 2D composite material actually comprises of the soft and brittle unit. And after the neural network, it just takes less than 1 second, and you can see the simulation very well. So this is a kind of a breakthrough work to me. So going back to my example, I'm not sure whether you can see this one. This is also the collaborative work with Casper. So we try to apply the FEA not on the robot, but on the sensor interface. We are using the FBG, making the FBG fiber optics layout, laying on the A4 size rubber in a very thin thickness, which is about 1 to 2 millimeters. So the profile is like this. The FBG fibers are laying like a dog bone shape layout. So we do a lot, some analysis why that has to be dog bone shape rather than rectangular or ellipse, because the dog bone shape can give a less variation, even apply the same deformation on the FEA. We found that the, let's say 28 FBG sensor laying along the clockwise direction like this, we found that the dog bone shape will suffer less variation. So that means we can have much more room to detect a more extreme deformation. So this is just a simple test why optimization for design fabrications. So we also do a lot of FEA in the virtual reality simulations and try to understand the string thread behavior when we simulate the deformation on the A4 size robotic skin. And how to do the training in reality. So let's say we put 9-point marker, which is the spherical marker, can be visualized by the 3D camera. We can't put too much, just 9 marker, but the FEA can do a very good job to provide a boundary conditions to interpolate more nodes within those 9 markers, and therefore we can have a more output. So in this diagram, you can see actually the input is the FBG data, 28 dimensions, and the output would be all the node points interpolated on the A4 size rubber. So now we got the trained data, and then now we put it in the practical use. And I can't say a very sophisticated sensor, but I can say this is a kind of a robotic skin for hyperelastic morphology detections. So with the training data, we can operate the FBG. This is just a single core, single pieces of FBG using the WDM interrogations. We can achieve 100 Hertz sampling frequency, and the position error tracking, which is around less than 3 millimeters. So in terms of validation, my student will go give you some technical details how they do the validations in the poster presentation sessions. So we also put the validation to a further extreme case. We try to see how that kind of sensor can encounter those kind of very impulsive force interaction deformations. So we spit some water on it, and I even fire the bullet from the DJI RoboMaster in a very rapid way, and then you can see we are still successfully detecting the vibrations and interaction with those bullets.
Kawai.
Okay, so I need to move on. So this is another example. We train the data in air, but put the robot skin in the water, and the deformation is still okay. And then finally, I may use these slides as a summary. I may not repeat all the content, but this is a paper I recently read it on Science Robotics. That paper even asked a very interesting question. What is the hard question for soft robotics? And then they try to classify the levels of contributions. If we focus the last one, level 3, very interesting one. How can we demonstrate the soft robot in? So this is a level 3 in this article. We try to use a surgical application as examples. Resonant that question, why that has to be solved, and how can we leverage the compliance to outperform the rigid solution in terms of patient outcomes. So this is a kind of I don't have a solid answer, but to my experience, I found that computational mechanics can be a very good tool to analyze the morphology, but not just analysis. That could be incorporated into the real-time control. Before, without AI, without deep learning, we don't have hope on the computational architecture. We never expect GPU, FPGA can accelerate in real time, but AI can bypass a lot of very complicated computational process and then make it like an optimizer to FEA procedures. So that's my presentation, and thank you very much, Casper. I hand over to you.
Fantastic. Thanks a lot, Kawai. I mean, brilliant overview of modeling and control of soft robots with many applications also, of course, in the medical field. I liked how you, went back and looked also at other systems being developed by other researchers. So yeah, fantastic overview. So we have time for a few questions. I'll read out the first one by Karthik C. Do you think model-free control using machine learning has the potential to completely replace all the methods you described today for controlling soft robots?
The quick answer is no, because model-less, model-based, they always have a pros and cons. But while you understand the application more, and then you are the one as a developer to pick the pros and cons based on your applications. So, for example, in surgical robotics, somehow, if we totally rely on model-less, model-free control, I can say that may be somehow difficult to ensure people to add confidence to the robot to ensure the safety at some point. So that may be probably we need the model, we need the geometrical model as a baseline to do things on top of that rough model. That is some kind of message I want to deliver, particularly for the surgical application today.
No, that's very good, and I think it's also very much in line with what I was thinking. And so I suppose what you're saying is have an analytical model, have a safe model, and then any residual aspects could be dealt with learning, with a machine learning approach. Yeah, fantastic. Yeah, thanks. That's totally aligned.
I guess that if we can achieve the analytical model easier, definitely we would do it, and then put the rest to the machine learning.
Yeah, good. So we have a few more questions coming up. So very nice work, Professor Kwok. I'm looking forward to reading it, probably your article when published. One quick question here: how do you quantify the force boundary, such as the laser water jet impact in the simulation? So what is the boundary of your force range?
Well, we didn't test it very well, but the boundary is that we try not to break the optical fibers. So that's why it may not be very stretchable using FPG. But this, honestly, I shape myself as a more on the computer scientist. This is a very I'm not the material scientist to fabricate sensor. I'm not good at it. But just a very interesting demonstration. If we can look at the machine learning, utilize a machine learning model, a machine learning method well, we can relax a lot of fabrication criteria. For example, this work we didn't need to lay out the bone shape fibers on the rubber very accurately. We even don't know the relative location on that A4 size somehow. We just train it. We just ensure FEA can do the job as a boundary condition of that rubber. So sorry, we didn't do a stress test on it.
Yeah, I think that relates also to the next question here. Thanks for that. So impressive work. The anonymous attendee says, is FPG sensor able to stretch? I suppose you answered that already. And that is also then the follow-up question on that. Is this the reason why you wrap around the FPG like a spiral? And I suppose yes.
For soft robot continuum example, yes, we wrap it as a spiral, and then the robot can encounter certain amount of extension due to that spiral along that spiral axial direction. This is okay.
Yeah. And then a follow-up from the same participant. How can the machine know the bending direction? For example, in case of the paper, I suppose this was your silicon material. So how do you compute the direction of the bending?
I guess you mean the bending direction of the overall sensor rather than the bending direction of the FPG. So if overall sensor, as I demonstrate, which is well trained with the 3D camera. So the 3D camera position as an output, FPG as an input. So in that training, the signals tell you what kind of signal pattern will behave to have the sensing behavior bending upwards or downwards. So we didn't specify negative or positive string data, which is relative to the bending upward and downward. We don't know it. We don't know it at all. So no prior knowledge on it. We don't need to specify it.
It just comes through the learning.
Yeah.
Good, fantastic. I have many more questions, but unfortunately we don't have the time. But yeah, great to see that overview. Thanks for being here, Kawai, and thanks for presenting. So you it's quite late at your place, yeah?
Yep. So 10 o'clock, but I'm still here. I try to do my best.
Okay, yeah. If you could stay for the rest, that would be great. So we have now a break. We are slightly behind time, but I think we should take a 5-minute break anyway. So if I can ask everyone to return in 5 minutes, that would be great. And also take the opportunity to look at the posters. Okay, I suppose we are slowly moving towards the second part of our workshop today. And I have seen already our next two speakers who have arrived. So Ariana Menchassi and Alberto Arezzo. And it's great that they are here today presenting about their work. They, together with Hongbin, were involved with the StiffFlop project that we had many years ago. And it's always great to see colleagues from these early starts, from my perspective, in medical robotics and soft medical robotics, to see them again and to hear about their advances in medical robotics, and in particular soft robotics, of course. So yeah, I think we are ready to get going again, and we have now Ariana Menchassi here. And yeah, really great that you have the time. And I have the feeling from the message you just wrote, you were rushing over to come to your to give the presentation here. So yeah, thanks for joining, and thanks for being here. I pass on to you straight away.
Thank you very much. Let me start with the sharing. And thank you very much, Casper, Helge, all the colleagues and friends from the old StiffFlop projects. It was a pleasure to rush, first of all, because I am in the same position. Sorry for the background, that is the old one. And it is always a pleasure to be in this community. Thank you for inviting me. So, okay. Okay, so today I will try to explain, to introduce our experience in medical robotics devices redesigned by a soft approach, as mentioned in the title. So together with my group and some colleagues, Alberto, will spoke after me, we are developing we have been developing different medical robots since 20 years. And thanks to the experience nurtured with the colleagues in UK and the project StiffFlop, we redesigned some of these medical robots by a soft approach. I'd like to start from this, let's say, organization of different robots depending on the modality of the interaction with the humans. So the human-robot interaction is a key for the design of robots, not only medical robots, but specifically medical robots nowadays, because the robots should be more human-centered. And so the modality of interaction with the humans is a key. It can be an assistance modality in the sense that the robot is something that you can wear and can assist the patient, the operator, during the normal daily life. Can be a cooperation modality. Nowadays, there are many examples of cobot, so robots that are partially teleoperated, partially autonomous, and they are sharing the same space, the same workspace with the humans, and they can be driven by the humans or they can drive the humans. And they can be used in teleoperation modality also. This is the typical operation that we have with traditional robots, for example, for endoscopy or for minimal invasive surgery, when the medical robot is a sort of extension of the human hands to enter small or narrow areas of the human body, to go a very in deep area of the human body, to enter the traditional orifices, and so on. In all these cases, the mechanical, regarding the mechanical design rules, interaction safety is very relevant, and it can rely on the use of lightweight materials or on the design of passive system. Or interaction safety can rely on the use of compliance structure in the design of actuators with variable properties. Regarding the design principle, in this graph that is very basic, we can organize soft design and rigid design by seeing that in rigid design, you have the top precision and top force exertion. With the soft design, you have top structural compliance and many degrees of freedom. This can be good or not, it depends, because when you have a high structural compliance, it means that if there are external forces, you are not able to maintain a certain position. So this is a problem in terms of precision. And the same for degrees of freedom. Having many degrees of freedom is good. People working on rigid design rules, they know very well that many degrees of freedom is something very difficult to achieve with traditional design. In the same time, many degrees of freedom means that you have major problems and control. So controlling soft robots is something that is not yet completely solved. What is in the middle? There is a gray area. Normally the gray area are something good or something bad. It depends on the viewpoint. The gray area is the area of hybrid, with the attempt to take the best from rigid design and soft design. This gray area is populated by different hybrid soft rigid designs. I have sketched just 4 of these soft rigid designs. The first one, top left, is rigid actuation with soft cover. You can see just an example of a traditional ends with rigid links, but on the tip of the link, you put some soft cover just to make the interaction with different objects a little bit more friendly, let's say. Another opportunity in the bottom left is soft actuation with rigid link. In this case, you have a rigid skeleton, let's say. You can have tendon-driven links, which can guarantee low inertia thanks to hydraulic soft chambers, which bend or merge passive rigid link structure, or thanks to tendon-driven system that transfer force from a distal actuator over a soft structure with rigid attachment points. Another possible design is on the top right, guided soft joints. In this case, you have, infinite degrees of freedom that is traditional for soft actuators, but these infinite degrees of freedom are contained, are limited by rigid structure to avoid joint bending in undesired direction. And finally, differential stiffness through the use of multi-materials. This is the last example on the bottom right. This is based on the combination of materials with low stiffness to enable large deformation and with high stiffness to increase the transmitted forces and stability of the overall structure. I like to present 3 different cases that are coming from the previous. They are a sort of, let's say, paradigmatic example of the previous design solution for hybrid soft rigid system. The first one is a tunable stiffness and shape changing actuator. For all of this system, I will try to explain why we, after a long experience on tunable stiffness devices for surgery, why we decide to apply what we learn in this specific actuation, in this specific application, sorry. So in this case, we were looking for simpler medical application after many efforts onto soft robots for surgery. I don't want to say that there are medical applications that are simpler and medical applications that are difficult. But for sure, all medical applications related to intervention with acute operation during a surgical operation, they are quite complicated in terms of safety, in terms of biomaterials, in terms of biocompatibility. While other solutions based on wearable system can be easier to be designed and also to be tested. So we have developed a sort of smart socket for lower limb prosthesis with the idea to compensate for volume and shape that can change during the daily life of the patient. You have to consider that the socket is a very relevant component of an artificial limb. Why? Because this is the interface with the human body. So if the socket is not comfortable, the patient refuses to have the artificial limb. And why there is these difficulties in finding comfortable solution? Because there are it's difficult to modulate the pressure and the shape of the socket. So in this case, we used our experience on jamming, layer jamming, and inflatable actuators for designing these bands that can become rigid or soft, depending on the specific operation of the patient. They can change the volume and the shape because there are layer jamming, and in between you have inflatable bags, so you can change the shape of your socket internally, and you can make the interaction more soft or more rigid depending on the specific task. So for example, you can decide to make your interface soft when you are sitting, so low stiffness, vacuum off for the layer jamming, and you can decide to have a nice stiffness with layer jamming on when you are walking. So in this case, a simple, very lightweight solution for socket internal active redesign can be a key for the acceptance of the overall prosthesis. So I have to say that I am not an expert of rehabilitation, but this is a need where soft robotics can really help, also for the acceptability of limb prosthesis. Another example where we applied very much our knowledge about soft hybrid soft rigid designs was the development of a pressure-driven manipulator with variable stiffness structure. Why we focused on this design? In this case, we were looking for hybrid variable stiffness solution after the experience on jamming technology. So jamming can be extremely nice for some application, but not for all application. But we discovered that the possibility to tune the stiffness of joints, for example, in a manipulator, is something extremely interesting for enabling many different operation modalities. So this is a very simple design, but with very nice performance. So this is a manipulator consisting of, okay, I stop here. This is a manipulator consisting of different modules. So you have a skeleton, a rigid skeleton, including 3 different joints, and we will see better the joints. Then you have an encapsulation layer. You have the pink part, the yellow pink part. They are soft actuators that you can insufflate for bending. And externally, you have a fiber reinforcement element. The key of all the design is the joint. Why the joint? Because the joint is a variable stiffness joint. So you can see an highlight of the joint. The joint is fabricated by a couple of structures with an internal part that is inflatable, as you can see here. So when you are not inflating the joint, the two parts can be moved freely. But if you inflate the joint, you generate some bumps that are blocking the joint rotation. In this case, you can freeze your device in a very specific position with very lightweight solution and very effective. So at the end of the movie, you can see some experiment just obtained with the skeleton. So you can see the three joints. The three joints are really small. If you pressurize just one joint, it is rigid and you can move around the other where you see off. In this case, you have two joints pressurized. And here you have three joint pressurization with a zigzag configuration, and the structure is completely rigid. So we developed a little bit more this idea by combining recently some sensor as proprioceptor sensor, and by working a little bit better on modularity. I cannot give more details now because this is a work still under publication, so this is confidential. But we developed a multifunctional model. So for surgery, but for manipulation, this is an actuator, let's say, with controllable stiffness with a solution of tunable stiffness joint as previously demonstrated, actuation in 3D with 3 actuators, and proprioception sensing based on inductive sensor that are based on some spring that are working both as reinforcement spring for the actuators and sensors. Now let's go to the last example. Hybrid soft-rigid joints again with guided soft actuators. So in this case, which is the motivation? We were looking for hybrid soft-rigid components as general purpose components for soft robots. I have to say, and I am really happy that there is Alberto online, Professor Arezzo online, because the original idea of this device was generated together working on the RED system that Alberto will explain later. But the RED system finally was fabricated with different actuation modality. But at that time, we were looking for some solutions, pneumatic solution, to be to fabricate micro manipulators to be put on the tip of an endoscope. And we are considering different fluidic actuation based on elastic fluidic solution and piston cylinder solution. In the first case, with elastic fluidic actuators, you have normally a very good compliance and a very good eye-back probability, but a low force. In the second case, with piston cylinder actuators that are solution very well known, you can have a large force and displacement, but you have many problems of sealing, especially in small size. On the other end, with fluidic actuation, there are very good solutions because you can obtain compact and efficient solution. Normally, they are very silent and lightweight, low cost, adaptable very easily to medical constraints, operating at body temperature and without electrical connection. That is very good in terms of safety. So the idea was to remove the problem of the seal and to combine the two families. So why not using fluidic actuators, but with an external body that is rigid, so that can guide the joint. With this solution, we developed roll joints and pitch joints, and we started to play with these joints together to build more sophisticated manipulators. As I mentioned, this solution was not used for the device for endoscopy, for surgical endoscopy proposed by Professor Rizza, but it was very, very useful as a general purpose component. So at the end of this presentation, which are the take-home message? First of all, the first one is this one. You have to understand the added value of soft robotics in specific application. This is the key for the success. So first of all, you have to wonder why robots in surgery? Why people have introduced the robots in surgery? Originally, robots have been introduced in surgery for being faster and more precise. So surgery using only soft robots can be possible or is answering to a real unmet clinical need. Maybe surgery combining soft design and traditional design are better. And this is what we tested, for example, combining a soft camera together with a Davinci system to obtain different point of view for traditional Davinci surgery. Or soft devices only for specific surgical tasks. For example, working with the clinicians, we developed some solution for retraction of organs based on magnetic forces and granular jamming that were really effective and small size. This is not for a complete surgical operation, but this is for a specific surgical task where you can identify the need that you can better solve with this soft solution. Hybrid solution or combination of different design and fabrication strategies is another key for success. So novel components that can be intrinsically hybrid can be the key in this case. I think that it's extremely important to have not only a robot, complete robot for a specific application, but for the evolution of a certain sector, you need components. So we are all using electromagnetic motors because this solution is technologically very well evolved. So you can buy many different electromagnetic motors with different gears, different sensor embedded, different controllers. So the possibility to have components give the ability to design many different solutions for different problems. So the ability of components intrinsically hybrid, it's a key for for boosting this this field of technology. And finally, as hybrid solutions are better, hybridization of ideas with colleagues is the last very important key for success. And I think that the Hamlyn Symposium in this case is one of the most inspiring events for looking at different problems, looking at different solutions, and hybridization of contamination and hybridization of ideas. So thank you very much for your attention. Thanks to the team working with me on these topics.
Fantastic. Thank you very much, Ariana. A brilliant overview of the different solutions in soft robotics around the world, but then also fantastic insight into the newest developments from your team. Yeah, I mean, I'm always very excited by seeing your work and always something new there. So thanks for that. Yeah, I suppose there will be a number of questions. I can see now one question already in Q&A. I can just read it out. Karthik C again, thanks for sending us the questions, Karthik. Professor Menchasi, could you please comment on the position accuracy improvement of soft robots with advances in nonlinear control? And then he continues also there. Some researchers are of the opinion that soft robotic control will eventually reach the control accuracy of rigid robots. What's your view on that?
So I am not the most expert person for control and nonlinear control, but yes, I have to say that in the last years we are experiencing the I cannot say the same precision of soft robotics of the traditional, of the rigid counterpart. Yes, but nowadays there is a very relevant evolution. What I want to say is that it depends on what you intend on precision. Because in a sense, if for precision, you mean that you have a target, you reach this target independently on the environment, this is not for soft robots. If you intend to reach the target by considering that you can deviate, so your target is there, but the trajectory can be different because you have to take care of the environment. It's a different concept of precision. So it depends what you need and how much is important to know the trajectory, the traditional robotic trajectory. So this is the same of our hands when we are doing something. If Professor Arezzo is operating a patient, he is very focused on what his tools and his hands are doing. But normally, I think it does care how the elbow, which is the configuration of the elbow to reach a certain area. So I think that it's very important to work on the improvement of the control, but not losing the focus. Because maybe we don't need all this knowledge of the trajectory.
Yeah. No, I do agree. And in your talk, you made a very strong point for stiffness controllability, but also I think a very strong point for thinking about hybrid approaches, linking the traditional rigid kind of type of robots with the more modern soft robots. And you spoke about the hybrid components, I think, but how do you want to go about that? So I mean, you mentioned the electrical motor, the electromotor, and how advanced it is and evolved, but how can we achieve something similar now in this hybrid world that you were proposing? How do you want to move forward practically there?
So I think that the possibility of having a stiff body with soft joints that you can tune in stiffness can be a winning solution for many applications. Even if some totally soft solution, very octopus-like, are very fascinating. In terms of applicability, for example, for rehabilitation or for surgery, they can raise some problems also in terms of cleaning, certification of the material, and so on. But having a body that is, for example, a rigid polymer body with the stiffness of the joints that can be controlled, and with a segmented body, this is something that can find many different applications. Obviously, if you have to make something that is intrinsically safe during when you eat something, okay, for sure you need a soft cover. But a rigid guide for flexible joints can be a good compromise.
Good. And I mean, coming back to this idea of components, I mean, are you suggesting that maybe industry should come or someone should come in and develop something that would allow researchers or developers of medical tools to take these components and from these components and build their robotic devices?
I think yes. I think that for the success of a certain actuation technology, you need components available as the Lego bricks. Let's consider piezoelectric actuators. Piezoelectric actuators are fantastic actuators, but for moving the piezoelectric actuators from the lab or ultrasound generator to real actuation, people invented the ultrasonic motors. The principle is the same. It's a combination of piezoelectric actuators, but it's a real smart combination. So low voltage, 50 volts rather than 1000. Combination of many actuators together, traveling wave. So this is not so straightforward. But now piezoelectric actuators are used because you have not to buy the ceramic and to start with gluing the electrodes. So this is an issue, I think, for all actuation technologies. For example, piezoelectric actuator can be better in the future than traditional electromagnetic motors. Shape and memory alloys, for example, we have not yet achieved this level of integration. You buy the shape memory alloy and you have to start with the characterization. And it's the same for our, say, stiff lock device or actuators. You have to mold, to use reinforcement fibers, you have your receipt. That is good for publication, but for having a boost, you need something more practical to be used.
So we have to push the TRLs up, the technology readiness levels, and have components off the shelf. Yeah.
Yes, components with high TRL. Yes.
Yeah. No, I think these are good points, and yeah, maybe not so interesting for those who want to write papers, but definitely will push the field forward, and especially with respect to applications. Yeah. Good. I don't see any raised hands. So then thank you very much again, Ariana. Fantastic presentation, and also, yeah, I think a great vision. Thanks again. And I move forward now to Alberto, last but not least. Yeah, Alberto Arezzo, great to have you here. And I look, and yeah, so yeah, good to have you here because we are all engineers so far, all the speakers. And I'm an engineer as well, of course. So it's good to have always the clinical view, because at the end of the day, we want to create systems that can be actually applied in the clinical field and can be used to help patients and the surgeons as well, I suppose. So over to Alberto.
Thank you, Casper, and greetings to the many friends I see connected here. It's a privilege for me to be here. I have quite a long presentation, but we can interrupt it anytime. I hope we can save some time for some discussion. You asked me to talk about the future of endoluminal therapy. And the history of endoluminal therapy started in the year 1993, actually, endoscopically, thanks to Gerard Buus, who unfortunately left us very soon, and dedicated all his life to the problem of how to approach similar lesions, polyps of the colon and rectum, from the inside rather than from the outside of the lumen. You have to know that till that time, the technique that was most popular and is still very popular is the one that was developed at St. Mark's by Sir Alan Parkes, who produced a manual of coloproctology in which he described transanal excision. And 15 years later, something that looked really not different from what found in the Pompeii, excavations after the eruption, was transformed into something really futuristic, thanks to the development of a very unusual technology by that time, that was placing a microscope inside the rectum. And Gerard Buis became really a star in our field because of the possibility to perform microsurgery, because we called that microsurgery for that time, for the precision we could afford with this technology, inside the rectum with stereo vision. Now, the challenges were huge, as you can imagine. So at that time, the first thing that he tried was to use staples. It was exactly the right time in which staples were developed. And the same technology is currently used now in many, many other districts. But he managed to perform the first clinical resections, as you see here, with these completely novel instrumentations that came from Russia at that time. Because of the difficulty to suture, it was really difficult to suture inside such a narrow lumen. And many, many animal tests were done at that time in Cologne and later on in Karlsruhe with his team till he came 1983 to the first clinical case. And he immediately understood that this required a lot of training due to the difficulty and a lot of dedicated instruments, such as this magnificent multifunctional device that in one instrument collected all the functions that generally you require for endoscopic surgery, avoiding changing the instrument too much. So with this one, you can cut, coagulate, rinse, and suck out blood or other debris from inside the lumen. Again, avoiding the need to change the instruments too much through the channels, but still see how complex the technique was. There was really lack of dexterity of the instrumentation. And you have to imagine that he performed in his life almost 3,000 of these operations. And here in Turin, we still miss few cases to reach 1,000 in a team. And we are considered quite expert worldwide in this technology, in the use of this technology. But what you see here is because of the huge training that he had, having been the developer of the entire technology. But would you consider this user-friendly? Frankly speaking, not. And the issue is basically how to suture the defect once you have cut out a full segment of the bowel, the colon or rectal lumen. As you see, for the difficulty to stitch and to knot, at that time, he proposed the use of silver clips. So a very clever way to prevent sliding the thread through the wall and avoiding the difficulty of performing knotting in such a narrow space with parallel instruments. So there are two messages that I want to give. The first is that you have to be user-friendly. And the second thing is that you have to be high-tech, but using low-cost, possibly, technology. Now, let's start from the beginning very shortly now to understand where are we and where we need to go if we want to approach endoluminal diseases through the anus or through other orifices. First, you have to know that you have to screen people, because if you screen the population, you have a lot of lesions that are found before they become invasive, and so they're suitable for endoluminal resection without extending the resection to other organs, to lymph nodes, to the entire wall or to the fat that generally surrounds the lumen. The States are much ahead Europe in this, but still they cannot reach what is considered the goal, that is the 80% of the population at risk. And this is challenging, but this is also a great difficulty because you have to consider that colorectal cancer is rapidly becoming the first cancer globally. And if you don't screen it, you will never be able to identify the lesions when they are at stage 0 or stage 1, which are those suitable for endoluminal approach. Otherwise, you really require then major surgery, and why not chemotherapy or other techniques. Now, today's screening is ideally performed through a colonoscopy, and this is absolutely not acceptable anymore. This is a technology that is more than 50 years old, and it has lots of cons in the sense that it requires preparation. It's really uncomfortable, undignified. It requires training, and it has also some risk of perforation, not to mention the need of sedation in almost all the cases. And so the compliance of the population to adhere to screening programs is relatively small. Now, in this field, Scuola Superiore Sant'Anna, as well as UCL and the team of Caspar Althofer, but also the Imperial, performed a lot of research with huge advances, both in the field of screening as well as in the field of endoluminal operative devices. And there are also a lot of attempts of coming to the market by many companies with their ideas, including again Scuola Superiore Sant'Anna, that developed the Endotics that you see here down on the right bottom corner. This we called this the E-worm initially, but they all failed. And they all failed for several reasons I'm not going to discuss now, but you have to know that even swallowing capsules did not solve the problem, because this way you're not capable of diagnosing that many lesions that you would like, because in the small bowel for which the capsule was invented, the lumen is virtual and the capsule does not need to be oriented. But in the large bowel, definitely the capsule needs to be active and oriented if you really want to have a screening of what's happening around. And here really Scuola Superiore Sant'Anna played a role globally, because they are involved in similar research now since more than 20 years. And I started working with them already 15 years ago, probably, when we developed inside the Vector project this first prototype of a capsule that could be steered thanks to magnets outside the body. And we were also able to demonstrate how precise can be the motion of that capsule in an animated colon. And as you see here in the graph, we could demonstrate also that trainees using the capsule performed much better in recognizing polyps than expert endoscopists with standard endoscopy. So probably the use of such technology could also help in reducing the need of training of the medical doctors, which is an issue today for more advanced procedures. And this is why the Endu project had a motivation, and the Endu project, led by Professor Paolo Dario and Arianna Menciassi and Gastone Ciuti, saw all this that I'm showing as a rationale. And basically what we wanted to create was a platform with a tethered capsule on a side with embedded small magnets, stereoscopic vision, a working channel to provide the minimum operativeness that today is also available through standard endoscopes. But the navigation had to be done through an external magnet that allowed the capsule to navigate inside the colon and to steer inside the colon, so that whenever you could find something to look at or to snare it out, like conventional colonoscopy, you were able to do it, as you see. And I think this was an excellent demonstration of how technology can help really changing today's practice in medicine. Now, this is not all theoretical. The project was ended just before the pandemic, fortunately, with excellent results obtained. And this is the last version of the prototype that still requires some minor improvement, in my opinion, but is very convincing on several aspects. As you see, you can easily advance also in a very tightly shaped tether. You can advance in the working channel any kind of instrumentation. In this case, it was a grasper, and you can target the grasper towards any target that you would like. In this case, a polyp. As you see, we could pitch the tip of the end of the capsule in order to orient the working channel accordingly. And these are the images of the review meeting in which my coworker Mauro Verra actually showed how to advance with the help of the navigation system provided through a Comau robot that was holding the external permanent magnet, the capsule towards the cecum of the inanimated phantom. And of course, the capsule embedded already at that time, so we are talking of 3-4 years ago, the most advanced imaging systems also to allow artificial intelligence and easy detection of polyps inside the colon, thanks to a work done by Dan Stoyanov at the UCL that was partner of the project. Now,
let us move on to the procedure. Diagnosed as neoplastic with very high confidence.
This is something that is now becoming standard in endoscopy in the most advanced cases. And as you see, it will probably soon replace completely the need to take biopsy and therefore to have an histology, because you can do it live in vivo. But still, I think that the working channel will be necessary to snare out small polyps, to inject solutions and other reasons. There is a similar project that is provided by the group of Pietro Baldastri in Leeds, and they also were able to demonstrate the possibility to perform semi-automated tasks, as you see here, like the retroversion, or they could navigate the capsule along small tracts of the bowel, still inanimated, or in this case, this is a real pig, but it was still very difficult to navigate it completely automatically towards the cecum in the pig. The same thing was done in cadavers with more success. And unfortunately, due to the pandemic, both projects are now not stopped, but let's say suspended. Hope we can go back and work on that again soon, because there is still a little bit of work to do before they can get to the clinical practice. Now, the second point of my presentation is, now that we know how to improve the screening and therefore how to probably motivate more people on undergoing screening and finally finding lesions at an early stage, what to do. Because today what you would do is still, in my opinion, still quite unacceptable, in the sense that in case the lesion is small, let's say below 2 centimeters, what you should do, you should try to lift it up and then snare it this way. And with the energy that the snare can deploy there on the tissue, you can cut and coagulate at the same time. Frankly speaking, I think this is quite user-friendly, requires some experience. It is not without any risk. And I would say, in a word, it's quite barbarian in 2021 to still use similar technology to do something on which really your life can change. And still, this does not answer to what to do to the larger lesions that fortunately we still do, benign, so suitable for endoluminal approach only, not requiring segmental resection of the colon and lymphadenectomy. So you see here at least a 6 centimeters lesion that you can still lift completely, but in any case, you will never be able to snare it out with a single snare unless you really create a perforation. It's obvious that you need a better way to remove these lesions thanks to tissue manipulation. Yes, because as I said, the early detection and removal of colorectal adenomas prevents the development of colorectal cancer. And it is very important to remove these lesions before they spread to surrounding organs. This is too clinical, I'll skip these slides. So in one way, it is important to go full thickness, because if you snare it out this way in many pieces, you will never be able to understand if what you have resected is benign or malignant, and in case it is malignant, how deep malignancy went, and if you could consider your treatment radical, curative or not. Now there is a trial that was designed by my friends in Amsterdam. This is Paul Fokkens, one of the top endoscopists in the world, president of the European Society of Gastrointestinal Endoscopy, and also of the United European Gastroenterology. Now, what he's doing, he is snaring in pieces a lesion that is very close to the anus, and he is now commenting about this brownish tissue that he's leaving here, that he is suspecting could be a remnant of the lesion, or even worse, maybe an infiltrated cancer. So we have to try to avoid this, of course. And in a prospective trial that they published some years ago, you see that in fact, we are not able to predict which lesions are really benign or malignant, which may sound difficult to believe, but this is how it is. And this means that in about 1/6 of the cases, we are not able to predict if the lesion is benign or malignant. If it's benign, you can snare it out in pieces, no problem. But if it's malignant, this is what happens. What do I mean? I mean that you may really run the risk of leaving cancer cells behind, and this is not acceptable. A correct way of removing these lesions would prevent this risk and would allow you still to have an endoluminal approach and not a radical approach. So it's already more than 20 years that endoscopists tried to do something, let's say, surgical-like, and I mean try to dissect large lesions, cutting around and below the lesion, as you see in this case. This is called endoscopic submucosal dissection. It's extremely challenging to resect something like what you see here, which is 2, 3, 4, maybe 5 centimeters in diameter, can take as much as 4, 5, or 6 hours. And it's very risky. And the reason why it's risky is the following. It's doing this procedure is just like cutting with one eye, because you are in 2D vision, with a knife in the center of your front, and you don't have any manipulation of the tissue that you're trying to cut. The only thing that will help you is this transparent cap that can, how do you say, distantiate a little bit the tissue. But tell me, can you really swear now that we are cutting exactly at the edge of the tumor, not too close to the tumor? Can you really swear that we are not cutting through the tumor? Can you really see exactly which is the edge of the tumor, and would you feel safe to go on dissecting things this way? I don't think so. Even in case of perforation or bleeding, it would be very difficult to manage those circumstances, in my opinion. I think you don't need to be a doctor to understand that what has been doing here by a friend of mine is wonderful, but at the same time, extremely risky and absolutely inadequate for the time being. So already many years ago, still with Gerard Bues, we tried to use again the same idea of stapling to dissect even large lesions, full thickness, designing this kind of endoluminal full thickness resection device, which was a stapler, like the one that I showed before, but governed completely transanally, with no need of laparoscopic or abdominal abdominal overview. But this is definitely not the way. We stopped that project already 20 years ago. And you have to know that the reason why we stopped that project is that Gerard Bues is also the inventor of robotics for surgery. He, together with Rick Satava, he is a pioneer on that too. And here is the demonstration of the Artemis robot that he used on living animals already in 1995. Now you have to know which was the motivation for doing that. He immediately knew, as pioneer of laparoscopy or endoscopic surgery in general, that by changing from open surgery to laparoscopy, in 1 second, the surgeon was missing all his degrees of freedom of his arm. The idea of robotics was not to make a more precise dissection, but the reason was to return to the surgeon the dexterity that he had the habit to have in the OR. In fact, if you think of a laparoscopy of endoscopic surgery performed through trocars like these passing through the abdominal wall, actually you have a pivot point, and you cannot have more than 4 degrees of freedom unless you use bendable, steerable instruments. And this is not corresponding to the 9 degrees of freedom that actually we do have in our arm. No better place to work on that than the Capsule Research Center at that time. And parallel to that, on the inspiration of our Artemis robot that actually was my PhD thesis I'm particularly proud of, the Davinci System was developed. They came to visit us many times at that time. And in the end, they produced that, to which we responded with the Radius system from the Tübingen Scientific, which actually is exactly the same architecture of the Davinci, but it's purely mechanical. And if you really want to know a secret, this is exactly the same patent that equips the Senhance robot, which is the first competitor of the intuitive system. The Senhance actually has a needle holder which is called Radia, and is exactly the same patent that Mark Schur for Tübingen Scientific allowed them to use. And this is a system with 7 degrees of freedom, but this is purely mechanical potentially, and this is meant to return to the surgeon the dexterity. And this is what I was mentioning before. This is Radia, the electrically driven version of the Radius system of the Tübingen Scientific. Just a matter of mechanics, nothing more. But the same thing can be done today with more simple instruments like the Hand X by Human Extension, an Israeli company, which is now also approaching the European market through B. Brown, that also has exactly 7 degrees of freedom, and it's a handheld device. You don't really require platforms to do that. Now, why would you use a robot instead? Well, which are the problems that still are not solved in laparoscopic surgery, in endoscopic surgery? Is there any field in which we could do better? Yes, of course. For instance, this is laparoscopy for rectal cancer. You see how often we cross our instruments, which is something not acceptable for safety reasons. And in this field, together with Kaspar and Arianna, of course, we started working first analyzing the limits of the intuitive Davinci as well, that has exactly the same problems because it's based on the same architecture, and in fact did not prove any benefit in this field, as you could see from the scientific literature. And thanks to the inspiration to the bio-inspiration to the bio-application, this was transformed by Kaspar into a fantastic experience in the StiffLop project that we performed together between 2012 and 2015. And Arianna has already commented on that with much more advanced things, so I will skip all this part of my presentation. And I will go back to the endoluminal application.
Alberto,
yes?
Sorry for interrupting. So we are approaching now 25 minutes.
Okay, I'm going to the conclusions. I'm showing the red system and that's it.
Thank you very much.
Okay, so I skip all the presentation done by Arianna, our project at that time. And I want to show you instead what is new in the field of endoluminal robotics. I do not mention so far the SP from Intuitive. I think it's still quite primitive and in fact not FDA approved. You know that there are several instruments that are currently under development, some of them since more than a decade. And I would like to concentrate on what it is today, my idea that I'm developing again together with Arianna and his team. And the idea is to create a cap exactly of these dimensions. As you see, it's 5 centimeters. It's 5 centimeters long and 2.5 centimeters large, a cylinder. that you allocate at the tip of an endoscope, and this allows you to have 3 degrees of freedom per each of the 2 arms that are embedded in this cap. And thanks to the geometry of the cap, we are able to lift and pull by more than 1 Newton, which is what we absolutely require. And I don't want to go too much into the technical details. I will just show you how the system works. This is how all the pieces were received at Scuola Superiore Sant'Anna, and this is the prototype once mounted on the tip of a standard colonoscope. And here are the 3 movements that are allowed for the hook, and the same goes for the grasper that is embedded in the cylinder as well. So that in the end, this is what is the result of prototyping there at Scuola Superiore Sant'Anna. This is the surgical tool. In this case, the endoscope is missing, but you see here the gripper arm that is now advancing. And this is the controller to standard Phantom Omni, modified with the handle of a classic laparoscopic instrument. And here you see the grasping thanks to a spring mechanism, the grasping of the tissue and the cutting of the tissue thanks to the pitch movement of the hook. Now, if I would stop here, you may think that we are back to the Back to the Future film. And no, I don't want you to think that I'm that kind of surgeon. I'm doing clinical activity every day. And I'm happy to present here in a minute, not more, Casper, what we were able here at the University of Turin, together with one company called Robotics, to perform clinically in the same field. I mentioned before that Gerald Bues invented transendoscopic microsurgery, which is a rigid rectoscope that allows you to dissect up to about 15 centimeters from the anus transanally. If you would be able to do the same using flexible shafts and flexible endoscopes, but with rigidity, of course, you would be able to extend the same benefits of transendoscopic microsurgery upwards to the entire colon. And whenever you see an early lesion, here is how the system navigates thanks to a Delta robot. Whenever you see an early lesion, you would be able to manipulate the tissue differently from what offers today flexible endoscopy. And you would be able to dissect it, cutting all around, and at the end also suturing. And this is what we are doing here. This is a case. I will speed up the video. We lift it. And once we have lifted, with 2 non-robotic instruments, which is currently the limitation of this platform, but thanks to the robotic endoscope, perfectly on target, and with stereo vision that you do not see here, we are able to cut very precisely due to the fact that we have a pivot point at very close to the target, so that the instruments in fact can flex of only for about 3 centimeters, which allows you to have a very good triangulation and very good control of the precision of your dissection. And here you see how easily you can dissect entirely below the lesion. And last but not least, in case you make a hole, the system has such a dexterity that you're also allowed to place a stitch with the system. I wouldn't say easily, but believe me, not in that difficult way as you could expect, and you could even knot endoluminally, avoiding the need to use those clips that I have shown you before. So I think this is a major advancement, but it's only a very small step towards the endoluminal application of robotics for surgery. And I think I would like to end up here saying that, of course, I would not dislike, as all of you, not only to improve dexterity, but also to improve automation in all the things that I have mentioned before. And in this respect, I think we are really behind the schedule, because none of the things that I've been showing to you today could be automated today and could not be easily automated in the near future. So I think this is a good investment. I would like to take the privilege to introduce to you my lab here 20 meters from my office, which seems more an engineering lab, I would say. Quite good equipped with a lot of instrumentation that is there to collaborate with any of you speakers today, and happy to make major steps forward in this field, because there is a great demand for that. And take the opportunity to say thank you to the many friends and colleagues that I used to work with in this field and allowed me to already achieve several results in this field. Thank you, Casper. Thank you, everybody, for your attention.
Many thanks, Alberto. Fantastic, fantastic way to conclude this day of the workshop, and really good to again to have your perspective, and to also show it in a very drastic way what the issues are, and what the best ways forward are. We are a bit over time, but if there's any burning question, I would like to invite that. Maybe I mean, in the spirit of this workshop, obviously we have the focus here on soft robotics. You spoke a lot about flexible robots and how they could, go further. But do you see also a need for soft, very compliant robots, or what's your view on that point?
Absolutely, yes. I think they should be steerable, but soft robots are mandatory. And to be honest, I could not disclose too much, but Arianna knows very well that now the new generation of the red robot is meant to become completely soft. I think there is also a fabrication issue, and at the same time also probably the use of pneumatic could be of great help. Again, I could not disclose too much, because one thing I learned, although I'm a surgeon, is that you should first protect your ideas before spreading them around. But there is an intensive work at Scuola Superiore Sant'Anna in cooperation with us on this. And yes, I think that you convinced me with the StiffLop. We were really at the beginning at that time, but I think soft robotics are a very good application for endoluminal techniques.
Okay. Yeah.
In this sense, we started with the idea to fabricate the red by soft robotics. This was the last part of my presentation. Finally, we developed the joints, but not ready for this, for the red system. So evolution now, we are coming back to the original idea. But it depends on the evolution of the technology in a sense. You need some steps to convince not only medical doctor, but also to convince ourselves as technicians that you can build something.
I heard you asking before how precision is important. To be honest, I don't think precision is that important in this. I think it's more important dexterity. This is what we are missing. Not really precision. It doesn't really matter if you cut 1 millimeter here or there, but the angle on with which you approach the tissue is more important than that. One thing. The second thing I would like to say, definitely all those instruments should be sensorized. I think we are a little bit behind in this. We know very well from the StiffLop project that sensorizing is an issue. Probably not that much sensorization is required as we thought at that time.
Well, yeah, thanks for that. I mean, I know we are totally over time, but I allow myself another question now that we have you here, Alberto. Thinking about automation, I mean, that is also a big word, key word these days. But what is your view on that? I mean, at the moment, you have shown us all these, very simple devices of the past with low dexterity, but also, of course, the need for the human to actually carry out these operations, and they are kind of like handcuffed when they have to do it inside the body. So to what extent do you think automation, more autonomous systems are important?
in the field of screening, automation is fun. It would be fantastic because this would accelerate so much screening, which will mean that we will not require that much resources to perform screening. In the field of operativeness, I think we have to avoid to make the mistake we did for several years in the past to completely automate a full procedure. I think we have to concentrate on which are the hard steps in each procedure and try to automate them in order to standardize them. Today, TEM is considered transanal surgery is considered very difficult because of suturing, not dissecting. So why don't we automate suturing? Suturing would open completely the horizon for transanal application if it would be automated.
Thank you. Thank you very much. Thanks, Alberto. Fantastic. And thanks for your view. I would like to thank all the speakers. We really have to wrap up now. But not all is lost. We have 2 more days to go. So I invite everyone to join us again tomorrow in this workshop on related to soft robotics for medical applications. And in particular, you mentioned it already, sensing was mentioned by you, and that will be our topic tomorrow. So soft sensors for soft robots. I hope I will see you all again tomorrow at 2 o'clock UK time. And thanks again to the speakers, and thanks for the audience for staying slightly over the time. All the best. Bye-bye, everyone.